The topic is slightly different from the original topic, but anyway, so it's related to some geometrical understanding of multidimensional data and geometric methods of machine learning. So just a few words about who I am. So I'm the head of research group in Skoltech. We work on deploying for 3D computer vision and predictive analytics. We publish in major conferences, and we collaborate a lot with various industrial companies like Airbus, Sberbank, Huawei, and others. And that's it. Just a very brief introduction about myself. And so let me now briefly discuss of what is the topic, what are the topics we will cover in today's lecture. First of all, I'll discuss why manifold learning and dimensional induction are very important. Why do we need geometric modeling of multidimensional data. Then we'll discuss some problem statements of dimension reduction. I'll introduce standard methods of manifold learning and dimension reduction. These are quite classic ones, but at the same time, on basis of these methods, I can easily explain important ideas used when geometrically modeling multidimensional data. And at the end, I hope I will have enough time, I'll tell you about a new, new research direction called topological data analysis. And based on a use case of time series prediction, I'll show how topological data analysis, which is another approach for geometric modeling, so how it can be used to model time series data. So that's it. Okay, manifolds. So actually, there are different definitions of what manifold is. But we are not interested in manifolds related to cars. We are not interested to manifolds related to this historic person. But we are interested in manifolds which are low surfaces embedded in high dimensional spaces. Actually, our world is multidimensional, and multidimensional data is difficult to use. Real-world data actually have low dimensional structure, and this is the reason why we can classify data, why we can solve regression problem. And what is important is that the world isn't flat. That is, although sometimes linear methods really work, but this is not always the case. And so manifold learning is a data analysis technology based on geometrical model about high dimensional data. First of all, the first statement, the world is multidimensional. Real-world data is represented by high-dimensional vectors. For example, an image is a high-dimensional vector where each coordinate is a pixel value of the image, and high resolution. So that means that the high-resolution image is modeled by a very high-dimensional vector or with coordinates equal to pixel values. Yes, and if we consider, for example, three-dimensional data, that is MRI data, medical imaging data, then the dimensionality can be even higher, especially if we consider functional MRI, because it's a sequence of three-dimensional images. It is well known from theoretical mathematical statistics that in general case, it's not possible to recover hidden patterns in high-dimensional data. Actually, it is a very well-known theorem of Ibrahimov and Hans-Minsky and Stone, who proved that if you consider a function or which lives in a d-dimensional space and which is Lipschitz, Imagine that we would like to recover this function from endpoints and data points. Then we can prove that the minimal possible, the worst case error, the worst case mean squared error of such functional reconstruction, it is lower bounded, so it is bounded from below by this value. And you see that, okay, of course this value goes to 0 if the sample size goes to infinity, but at the same time, if the dimensionality d of the input space is very big, then the speed of convergence to 0 is very low. Actually, you need exponentially many samples to reduce the error to 0. So, and this lower bound is non-asymptotic. The same case is when you estimate, when you perform kernel density estimation. So the minimax mean square error is all lower bounded by this value. So in general case, that means that it's not possible to perform estimation in high dimensional spaces. However, there are a lot of you know, examples, especially modern examples, when we apply convolutional neural networks, when we apply for image processing, generative adversarial networks, and we can generate images in very high resolution. So on the one hand, this mathematical result means that it's not possible, but on the other hand, we see that it's possible. I mean, these practical examples tells us that still it's possible. So why? Which properties of real-world data help and how? And actually, today we'll talk a little bit about such properties that are called latent structure models and low dimensional structure of data support. These are properties of real-world high-dimensional data which help us to perform inference from multidimensional data sets. Another statement is that real-world data has low dimensional structure. So that means that data from natural sources often it occupy a small part in the observation d-dimensional space. That means that actually the data has small intrinsic dimension. That is, it can be you know, it can be modeled using not the initial number of coordinates, not the initial number of parameters, but it means that this number of parameters is too big, and we can use smaller number of parameters to describe variations in data. And so this is an example. So in a minute or so, I will provide more detailed examples. So here you see some image in the initial resolution, but which contains around 10 to the power 6 pixels. But actually, it's possible to represent this image using only around 100 independent parameters, so that the quality of reconstruction of this image is still quite good. What we need actually? Actually, we would like to find the low dimensional structure of data. First of all, we need to estimate a real intrinsic dimensionality of the data. That is the number of independent parameters that are necessary to describe all variations in the obtained data set. This is the first thing. The second thing, we would like to construct enhanced dimensional features describing our data set with high accuracy. So that means that we would like to construct somehow the function h that can map any vector x into an s-dimensional parameter z, such that this z contains all information about the initial data set. And if we succeed to solve this problem efficiently, then we can use this extracted low-dimensional structure to solve specific data analysis tasks. Because actually, as it follows from the result of Khasminsky, Ibragimov, and Stone, if the data set is too high dimensional, then formally it's not possible to construct regression, it's not possible to perform classification or kernel density estimate. But if you are able to reduce dimensionality and describe your data set with small number of parameters, then of course you can use these parameters to as input features to construct the regression function. And actually, these kind of more approaches have been known for a lot of time already. The most famous one is principal component analysis. So, for example, I'll talk about principal component analysis a little bit later in more detail. Now, I just would like to briefly explain that, okay, we have an initial image of which is described by around 2000 pixels. So it is described by a vector of the dimension 2000. And what is interesting, we can approximate this image as a linear combination of images of the same resolution with some weights. And so such that we approximate this image with quite good accuracy. In this linear decomposition, each term is a so-called eigenphase. So actually, this is the eigenvector of the corresponding covariance matrix. So in order to calculate this vector E, you need first of all to take a sample of images. Each image is represented by a vector of pixels. Then you calculate covariance matrix, which contains covariances between coordinates of these vectors. And then you calculate the first several eigenvectors corresponding to the highest eigenvalues, right? And actually, each such eigenvector, it has the same dimension as the initial vector x. And so, because you know to which pixel, which coordinate of this vector belongs to, you can you can just reassign each coordinate of this eigenvector to some pixel value and represents the eigenvector as an image, right? And what is interesting in this example is that such eigenvectors represented as images, they have quite interesting, shape. You see that they are represented as so-called eigenfaces, and any face can be, decomposed as a linear combination of these eigenfaces. This is an empirical result, but a very similar, considerations are used when we process general types of data. So all this means that for any high-dimensional vector x, we can use a small number of parameters and a special decomposition. In this case, these are orthonormal vectors, so that each high-dimensional vector from our collection of vectors we can represent by a lower dimensional number of parameters. And then we can use this for any data analysis tasks. So, and formally that means that we approximate each object by a linear hyperplane which is represented by some average phase plus some linear combination of variations with respect to this average phase. Right? That's it. So on this example, you see that this is the original phase, and these are its approximations which you obtain when we use a small number of parameters, like 84 parameters, 40 parameters, or 20 parameters. So of course, the smaller number of parameters we use, the less accurate approximation we have. But at the same time, even with 40 parameters, the approximation of the image is quite good. But of course, the method, as you see, is linear, and in practice, we should use nonlinear methods because our world is nonlinear. And let me explain this using the following example. Let us assume that we have a video stream. This is the stream of frames. Okay, we have two consecutive frames, and we would like to predict, to interpolate this stream of frames, and we would like to estimate what frame we have here, right? Before going into detail, before discussing this, let us consider some toy example. Of course, it's not possible to, we humans can see only in 2- or 3-dimensional space, right? And so here, each object, I mean each image, it is a very high dimensional object represented by a high dimensional vector, where each coordinate is a separate pixel of the image. Let us, because we cannot see in high dimensions, let us assume that these points here, these 3-dimensional points here, they are actually images, right? So each point here is some image. From this image, we see that actually many pixels here, they have a very similar, very similar value. So that means that there are significant correlations between different pixels of images, of the image. They are very similar. And so that means that coordinates of a multidimensional vector describing this image, these coordinates are not distributed just uniformly in some intervals. They are dependent on each other. That means that if we consider all different images as high-dimensional vectors in some high-dimensional space, these high-dimensional vectors will not fill in the whole high-dimensional space. Say, they will not be distributed in this hypercube uniformly. All so vectors corresponding to images will group in this hypercube along some, along some nonlinear surface, because of the dependence between coordinates of vectors representing images. Okay, let us assume that this is exactly the surface across which these core vectors representing images, across which they are located. The question is how to estimate distance. Of course, we can take some point here and imagine that we would like to estimate the distance to the point here. So that means that we would like to estimate the distance between two images. And if we don't take into account the dependency between coordinates, that our images, I mean, each point here is an image. Of course, this is just a toy example, but this philosophy, it is the same for real-world examples as well. So Okay, and if we don't take into account dependency between between coordinates, then in order to estimate distance, we just calculate the Euclidean distance between this point, and that's it. However, in case we take into account the distance, the surface across which these points are located, then we should, we should go along this surface to calculate the distance. We should take how these points are located in the high dimensional space when we calculate the distance. And so, because of this, although formally the distance between this point and this point is smaller than the distance between this point and this point, right? But when we calculate the distance taking into account this nonlinear surface, then we will get that, okay, the distance here will be like this, but the distance from this point to this point, it will be it will be like this. So you see, it will be significantly bigger, right? Because we should take into account the surface along which the points are located. So this is the fundamental issue. And if we just use a linear interpolation between consecutive frames, that is, if we just calculate the linear combination of the frame alpha x1 plus 1 minus alpha x2, right? So if we take just a linear combination, that this is the same as if we consider linear interpolation. Then the result of interpolation will look like this, which is, not good, right? But if we take into account nonlinearities, that our frames as multidimensional points are located across along some nonlinear surface, then we can get reasonable interpolation. And the question is how to do this, how to recover the nonlinear surface where our observations are located, how to estimate from data properties of this surface called manifold. And as you see from these toy pictures, actually we need to take into account nonlinear dependencies. So of course, as I said, in practice, there are a lot of cases when just linear methods like principal component analysis, when these kind of methods work. But in practice, we need to take into account nonlinear dependencies. Yeah, that's it. And actually, there are a lot of papers. So these are just some, I would say, quite old papers. And nowadays, there are even more papers when people model manifolds using neural networks. So here, they used mainly first generation of manifold learning approaches, and then when we after we model the manifold, then we can solve regression, classification, and some other predictive modeling tasks. Nowadays, for this aim, we often use neural networks, but the ideas are the same. What is interesting is that even in real life, you can obtain data belonging to manifolds very easily. Imagine that we have a big office room, where we have this type of a robot with a camera on it, and then this robot moves along in the room and along some trajectory, and for each position of the robot, we obtain an image from its camera, in a specific position and from a camera with a specific view angle for different view angles. In this case, it's obvious that all images obtained in this way belong to a manifold which is parameterized only using several parameters. Two parameters are a geometric position of the robot in the room, and other parameters define view angle of a camera and its rotation angle. So that means that this manifold, this data manifold, is 3 or 4 dimensional. So this is an example of a real-world manifold of data. In general, we will be dealing with a manifold covered by a single chart. So actually, you can think about a manifold as a nonlinear surface in the initial d-dimensional space, such that coordinates of points on the surface are given by some nonlinear function and a latent vector z. So latent vector z can be considered as a vector with coordinates in a local coordinate system. So if you have a nonlinear surface, then some points on this nonlinear surface is defined by a vector with local coordinates z. And coordinates of this point in the initial space is obtained through this nonlinear transformation. In manifold learning, we need to first of all somehow estimate the inverse function, so-called embedding function. That means that using this function, for any point, any multidimensional point x, it can be projected on the manifold, and we obtain its lower dimensional representation using coordinates in the local coordinate system. So this is the first thing. And the second thing is that, of course, we need to estimate the function g itself and latent representations of all points in our sample as well. This task is unsupervised learning. This task is unsupervised because in practice we have only a set of points x. So statistical analysis of manifold valued data, it can be formulated as follows. Let us assume that we have some unknown probability measure on unknown s-dimensional manifold M with unknown value of this measure. We are given a sample of independent observations. So this sample contains n observations. Using this sample, we would like to estimate intrinsic dimension of the manifold. This is the first thing. That is the number of parameters which define this nonlinear surface, nonlinear manifold. Also, we would like to estimate low dimensional parameterization H on the manifold, to estimate the manifold itself, and to estimate the tangent space. So for some applications, it's important to estimate also the tangent space to the manifold. And also we may need to estimate a density living on this manifold, because if you would like to generate, for example, images of faces, or we would like to generate, I don't know, some other types of images, say images of cats, then of course these images they are located on some image manifold, but not all parts of that image manifold corresponds to cats. So we need somehow to model density on that manifold, and this is exactly what generative adversarial networks do. This is the reason actually why they works. And as soon as we estimate the data manifold and parameterize it somehow, we can perform, we can solve such problems of data analysis as denoising, super resolution, classification, regression, anomaly detection, and others. This is the standard. You know, pipeline. Also, I'd like to mention that there exists another very closely connected topic, which is called dimensionality reduction. So actually, manifold learning and dimensionality reduction, this is almost the same. In dimensionality reduction, they also work with high-dimensional objects like images, with various geometric descriptions of with various high-dimensional descriptions of geometrical shapes, with curves, speech signals represented by a number of high-dimensional points. And actually, in this presentation, I will show you examples based on these toy data set, MNIST. Everybody knows what MNIST is. Very convenient data set to show various how different methods work. And dimension reduction, it is, I would say that dimension reduction is a part of manifold learning. So in dimension reduction, mainly we would like to represent a high-dimensional, we would like to represent a high-dimensional object X by some lower dimensional object description Y. So dimension of which is significantly smaller than the dimension of object X. So in such way that we keep important information about the object X. So if we reduce dimension, we would like to keep as much information as possible about the initial object. So I would say that in this respect, dimensionality reduction is a part of manifold learning, since in manifold learning, in case of manifold learning, you need to make to solve some other important problems like estimation of the manifold, estimation of its parameterization, and other important things. Okay, so and now let me discuss standard problem statements related to dimensionality reduction and manifold learning. The first, I would say, standard dimensionality reduction problem statement, or also called embedding problem, can be described as follows. So we have a sample with n points. Each point is a p-dimensional vector, and we would like to construct an embedding which for each point x from this sample returns some point y with the number of parameters q, which is smaller than p, such that this new set of points consistently represents the initial set of points x. So I would say that these problem statements is the most widely used in practice. And the set y should preserve some geometric structure of x. And in different methods in this domain, they differ in how this requirement consistently represents how this requirement is formulated, because we can formulate this requirement in many different ways, and different methods use different formulations. Before going into details, let me show you an interesting example. So imagine that we consider a big set of images called ImageNet. So ImageNet is a well-known data set, and it contains more than it contains several millions of images. We first did the following pre-processing of these images. We take a big neural network called VGG, and we train this neural network to classify images into different classes, such that we can classify what object is in the image, whether it is cat or dog or tree or something else. This data set, it contains more than 1,000 classes. After we trained this neural network, we reprocess each image using this neural network and calculate features from the last layer of the neural network. These are so-called VGG features, and they can be used for semantic characterization of images. They have some interesting properties. That is, if two images are similar, then the corresponding vectors from the last layer of this neural network, these two vectors will be also close, geometrically close. After we represent each image in this data set using this high dimensional vector, its dimension, by the way, is around, as far as I remember, this 2048. Then we project each such image into two-dimensional plane, and this cloud of points, this is some subset of ImageNet, where we process each image using neural network, and then we project features on a two-dimensional plane, right? That's it. And now let us look closer on this cloud of points. So we take some part of the cloud of points and we zoom in some part of this cloud of points. And now let us see what images correspond to each point in this cloud. Here is it, very interesting results. So all points which are close, they correspond to flowers. Let us look at another part of this cloud of points, and in this case we get people who wear glasses. And if we look at some other parts of this cloud of points, we get so these are nails. Yeah. So what we get from this example, we see that it's possible to encode each high-dimensional object, high-dimensional image, with a lower dimensional vector. In our case, it is just two-dimensional vector, such that all points which are close, they correspond to images which are semantically similar. This is quite interesting result, for example, and this, for example, can be done in the following way. Let's imagine that xi and xj are high-dimensional vectors representing images. In our case, these are vectors calculated by the neural network. We calculate the distance between these vectors, between vector xi and vector xj. And this is exactly the distance between images in this initial high-dimensional space. As I said, it is 2048. And then we would like to represent each image by a two-dimensional vector y. such that if the distance between these vectors is small, then such that if the distance between initial vectors is small, which means that these two images are semantically similar, then the distance between these lower dimensional representation is also small. And actually, we can, formulate these requirements in this way. We take this distance and compare it with the distance in the new two-dimensional space. And then we optimize this functional with respect to vectors yi, yj for all pairs of images such that this functional is small. And in this way, we can get this two-dimensional projection with this interesting property. What is important is that we can visualize images by using two-dimensional points, and at the same time we keep semantic relations between images. Actually, this is a very classical approach. I mean, multidimensional scaling, which optimizes this functional. But nowadays, there are a lot of other approaches which allow to model nonlinear manifolds quite efficiently. And in order to do this, we need to formulate so-called extended embedding problem. So extended embedding problem, it can be formulated as follows. In the same way, we have the sample of points x1, xn. This is a sample of p-dimensional vectors, and we would like to construct the embedding transformation H, which not only transforms this set of points into the another set of points y, such that each point y has a lower dimension, but also this transformation H allows us to transform the point x, any new point x, to a point y. So that means that here we should construct an out-of-sample transformation H that can be used for this task. Exactly in this case, in order to solve these, to fulfill these requirements, we will need this manifold data model, which I already mentioned. That is, in the manifold data model, we assume that each point x can be represented as a nonlinear function f, which depends on some lower dimensional point representation b, maybe plus some noise, because our real world data is noisy. If somehow we can construct such a manifold data model, that is, recover function f and lower dimensional representation b, such that our data can be accurately approximated in this way. So if we are able to do this, then based on this manifold data model, we can construct this embedding function, which works out of sample. First of all, let us formulate a full dimensional reduction problem. This formulation is the most general one. So we have a sample x1, etc., xn of p-dimensional vectors, and we would like to construct an embedding transformation H that for any x returns a vector y of lower dimension. And also we would like to construct a reconstruction transformation G, which for any y can recover the vector x in the initial p-dimensional space, such that the combination of the decompression and reconstruction transformations is close to the initial vector x for any x from the considered data sets and from the considered data generation process. So this requirement means that we will not lose a lot of information when we compress a vector x and when we reconstruct its initial value. Schematically, this can be represented as follows. We have a data reduction procedure. So it consists of two parts. The first part is a compression procedure and the reconstruction procedure. And compression procedure compresses a full dimensional description x and obtain a lower dimensional description h, and vice versa. And the requirement is that the reconstructed h vector is close to the initial one. And now let me briefly show how we can use these ideas when we develop methods of dimension reduction. By the way, I got several questions from the audience. The first one is what is the latent space? So actually there are different different notions and different ways how the reduced dimension space is called. And often in some applications it is called latent space. In some other applications we can call it like reduced dimension space. For example, in case of principal component analysis, vector coordinates in the space of principal vectors, principal components. These coordinates are, also can be called latent parameters. So let me briefly remind you what principal component analysis is. In principal component analysis, it's a very old method. At the same time, still it is very, very efficient, and many applications can be solved using this approach. So in case of PCA, we model any vector, multidimensional vector x, as a linear combination of some principal components E sub j. These are basis vectors in the initial p-dimensional space, and we consider its linear combination to represent the initial vector x. In order to estimate these principal components, we take a sample of endpoints and we minimize the sum of squared residuals between each vector xj and its projection on the linear hyperplane defined by these principal components. And if we use this definition of the hyperplane and put it inside this sum of squared residuals, then we will obtain a simple expression which is the quadratic form, and the matrix of this quadratic form is exactly equal to the covariance matrix of these vectors. And so that means that optimization of this function is the same as calculating the eigenvectors of the covariance matrix. And these eigenvectors, they will be oriented in directions related to the directions of the highest variations in data. So, for example, if we have a two-dimensional cloud of points, then the first eigenvector will look in this direction, the second eigenvector will look in this direction, and we can use coordinates of each point in this new coordinate system to represent points instead of coordinates in the original coordinate system. And so if we don't care about variations along the second eigenvector along this direction, we can encode position of each point using only one dimensional coordinate. And that means that instead of using two coordinates to represent each point, we will use only one coordinate to represent each point. However, if in case of MNIST, if we project each image from the MNIST data set with a handwritten digit to the two-dimensional space of principal components, we will get a picture like this. So each point here corresponds to an image from the MNIST data set, and each color, this color denotes a specific class, because in this data set we have like 10 digits, so we have 10 classes, and we have 10 colors representing these classes. And in practice, we would like to have all points with different colors located in some different parts, in different parts of this two-dimensional plane, so that in these new coordinates it is easier to classify points for corresponding to different classes. But using, as you see, using principal components, it's not possible. Okay, I think I'll skip this example with principal components and faces. Multidimensional scaling, which I already mentioned, it is when we minimize the distance between when we would like to approximate the distance between objects in the original space using some lower dimensional coordinates in a new lower dimensional space, so that the distance in the original space should be approximately equal to the distance in a new space. And so we minimize this with respect to these lower dimensional vectors y. What is interesting is that solution of this optimization problem is equivalent to standard principal component analysis if the distance between objects is calculated as a Euclidean distance between their vector descriptions. But in many applications, it's not possible to do this, and so the only thing we can do is to define the distance between objects as it is. For example, in social studies, we don't know exact vector representations of objects. We can say only that this object is closer to this object, say two times closer to this object, and that's it. And using such considerations, we can define a pseudo matrix of relative distances and apply multidimensional scaling to project these objects and represent them as points in a lower dimensional space. There exists another variant of MDS called Salmon mapping. However, it is the only difference is that here we normalize with respect to the distance in the original space, because we want to, you know, we introduce this weight because if two objects are close in the original space, we would like to represent this property as accurate as we can. And so we introduced this additional weighting here. And now let us look whether this helps or not. Unfortunately, in case of missed data sets, whether it doesn't help at all. So if we apply PCA or we apply Salmon mapping, we don't get accurate, accurate projection. And as I said, this is because the real world is nonlinear, and somehow we need to model nonlinear dependencies between coordinates of vectors representing objects. Nowadays, often neural networks are used for this, and they exist so-called approach based on replicative neural networks, so autoencoders, or, for example, variational autoencoders. So these are approximate, very similar neural network architectures that can be used for this task. However, I would like to to discuss two other approaches, namely approaches based on local considerations and approaches based on topological data analysis. So I think I'll skip replicative neural networks. I will just briefly mention that replicative neural networks, it is it is a special approach when we represent the compression transformation using some simple fully connected neural network, and we represent reconstruction transformation also using a simple fully connected network, and then we try to train parameters of this left part of the fully connected network and the right part of the fully connected neural network in such a way that if we take as input some vector x, transform it using these neural network modeling compression transformation and then transform it using this part of the neural network modeling reconstruction transformation, then as input we get a very similar vector which accurately approximates the input. So as I said, this is some fully connected network for compression. This is some fully connected network for reconstruction, and then we train these neural networks simultaneously to achieve good compression, decompression accuracy. And as output of the compression network, we get a vector of smaller dimension, which helps us, which can be used as a vector of latent coordinates representing the object. However, as I said, nowadays there are a lot of modern architectures based on this idea, but let me consider some other approaches to manifold learning, which people also often use. And these approaches are based not on neural networks, but they take into account special local properties of data living on manifolds. So actually, there are a lot of various approaches for that, but today it's not possible to cover all approaches, so here is some list of such approaches, and today I'll briefly discuss two of them, namely IsoMap and local linear embedding. So these I would say are two most well-known approaches, and ideas and the main ideas of manifold learning can be illustrated on basis of them. All these approaches start from the same step. This step is related to construction of the graph representing local neighborhoods between points. The idea of this step is very simple. So we have a set of endpoints, and we would like to, to construct local neighborhoods. We do this as follows. So we take some point xi from the sample, and we construct a sphere of a radius epsilon with the center in this point xi. Okay, and then we construct a graph of how the points are related to each other. For example, these are our set of points, and we connect two points by an edge. If this point is in the local neighborhood of another point, of this point, and vice versa. So point xi should be in the local neighborhood of the point xj, and the point xj should be in the local neighborhood of the point xi. And then we also can define weights. So the simplest case is when the weight is equal to 1 if there is an edge between two points and it is equal to 0 in other cases, but also we can assign not only 0, 1 weights, but also we can use weights proportional to the value of the distance between points. In particular, we can use weights equal to the exponent of the minus distance between points. So this is the graph representing local neighborhoods between points. It contains information about the local structure of the manifold. So the main idea of the ISAMAP is to infer a distance matrix using distances along the manifold. Remember that, recall that initially when we discussed ISAMAP, when we discussed multidimensional scaling, in case of multidimensional scaling, we take initial distance between points, like this distance, yeah, just distance estimated in the initial Euclidean space, for example. And then we tried to construct lower dimensional representation of points in such a way that the distance in the initial space is accurately approximated by the distance in the embedded space. However, as I already mentioned several times, it's not correct to calculate the distance in this way, right? We need to take into account that our data belongs to a manifold. And so in case we know the manifold, of course, we will calculate the distance by moving along the manifold. But of course, in practice, we don't know the manifold. And so the question is how to approximate this distance. And the idea is very simple. The idea is as follows. This is our graph representing which points are related to which points, right? And so actually it can be proved that if we calculate the distance as a shorted distance in the graph connecting points, then this distance can accurately approximate the distance along the manifold. Of course, the more points on the manifold we have, the better approximation we get. But in practice, this is, you know, quite intuitive result. But anyway, the main important idea is that instead of calculating a standard distance between points xi and xj, we should take into account the data manifold when we calculate this distance. And for that, we construct the graph of how points are connected, related to each other, and then we calculate all distances as shortest paths in that graph. And this, to a significant extent, helps us to approximate distances calculated along the manifold. This is the first step. And the second step, after we calculate distances not in the initial space, but when we calculate distances in this way, we apply a standard multidimensional scaling approach. And that's it. So we try to find such lower dimensional space Y, such that the distance matrix in this space Y can accurately approximate the distance matrix calculated using this graph of points. And here is the result we get when we apply this method to MNIST data. So this is the result when we apply standard multidimensional scaling to MNIST data. You see that all points are, you know, all classes of MNIST data set are mixed. However, this is the result which we get when we apply ISAMAP to the MNIST data, and you see that classes are separated, which is very good. Another example, these are images with, you know, with a hand in different poses. And we project these images into a two-dimensional space. So each point here corresponds to a specific image of the hand. And we can see that here close points here corresponds to images with the hands in you know, the same position. So this is so from this example we see that actually this simple trick, when we calculate distances not in the original space but when we calculate distances and across the graph, helps us to incorporate local structure of the manifold, and this helps us to get more meaningful results when we perform projection. That's it. And another method I would like to briefly discuss is local linear embedding. So the idea behind this method is very interesting, although it is very, very simple. And so the idea can be formulated as follows. This is our cloud of points, and for each point from this cloud of points, first of all we find its k nearest neighbors. This is the first step. The second step, we take each point xi, this is the point from our data set, and we try to approximate it using a linear combination of its k nearest neighbors. These weights here are called barycentric coordinates, so they contain information, these weights contain information on how locally the manifold behaves. So we minimize this criterion with respect to these weights, and for each point of the data set we find its barycentric coordinates. And the last step is that, okay, we fix barycentric coordinates and we minimize these functional with respect to lower dimensional vectors y. So we would like to define for each point from the data set its lower dimensional projection y, such that this projection has the same barycentric coordinates for its k nearest neighbors as in the case of the full dimension. So this is the idea. We would like to keep this local structure of the manifold by keeping local barycentric coordinates, and we can easily do this by minimizing these functional with respect to y, and that's it. And here is an example. So this is the data set of images with lips, and we see that if we project these images on just a two-dimensional space, then close points in this projection, in this cloud of points, corresponds to semantically similar images, which to some extent prove that this projection is meaningful. In case of NIST, the results are not as good as in case of using ISOMAP approach, but this is what we get. And actually, in practice, often we just take several methods and try to apply it one by one to get results, to get the most accurate results. Okay, that's it. And now I have actually quite enough time to discuss a little bit another, another important thing about manifolds, so-called topological data analysis. So let's just, make kind of a conclusion. So I discussed why manifold learning is important, and I formulated several problem statements and explained what kind of methods we can use to solve these problem statements, how we can estimate manifold, how we can estimate embedding, how we can estimate some local properties of the manifold. However, there exist some other important local properties of the manifold, some other important properties of the manifold, invariants, which also can be used for data analysis. And topology is exactly a mathematical tool that helps us to define these invariant properties. Before going into details, first of all, let me answer several questions from participants. The first question is, why TSNE isn't used for data reduction, however it is used to represent the images into latent space? Well, I would say that TSNE works really nicely in case of visualization. And in principle, it can be used for data reduction as well. I don't see formally, I don't think that there are anything that can prevent us from using TSNE for data reduction. However, I believe that formally TSNE, it doesn't have specific theoretical properties that guarantee that corresponding embedding we obtain is good for data reduction and the solution of some downstream data analysis tasks. And some of the methods I presented, for example, local LLE or LTSA. LTSA is another method called local tangent space alignments. So these methods have such properties, and in practice, often they works better for data reduction than TSNE. Another question is, how deep you would know geometrical manifold theory for application of these methods in computer vision? Well, I would say that if we would like to, to construct some manifold learning method or apply it some existing manifold method in computer vision, you don't need to, to study the whole course of manifold theory, of differential geometry, of topology. You don't need all this deep mathematical knowledge. What you need maybe is like half-year crash course on basics of these disciplines. So you need to know standard definitions of, for example, differential geometry, maybe some main results of differential geometry, the same for topology, and that's enough. And this should be enough. In principle, they exist short courses on these topics in the internet, various overviews. So I think this should be enough. I see. Yeah, and I think that my colleagues will send to me more questions from you guys, and I will answer these questions after I present the last topic of today's talk related to topological data analysis. Okay, I will discuss this topological data analysis not just as it is, but in relation to an applied problem of demand forecasting. So as usual, we have lots of customers, limited resources, and we would like to identify available customers and predict, demand in order to optimize marketing campaign and other things. The problem is that we could have millions of time series, and we cannot construct for each time series specific features and then apply, for example, gradient boosting. So we need to have some automatic algorithm that can be used to predict all these millions of time series. And because of that, we need to have some unified automatic tool for construction of features that are sufficiently powerful for time series prediction. In practice, often managers solve this problem using so-called RFM concept. So RFM concept, it is the concept of estimating characteristics to characterize recency, that is, when was the last time that that user was active. Also frequency, how frequently has a user been active, and monetary, how much revenue has this user generated. So we assign 3 scores to each user, and then we can predict, and then we can, think what would be the future behavior of a user. However, this approach isn't very accurate, because users in practice can have different behavior. For example, one user or orders of the one user looks like this. So this is time, and these are moments of time when a user orders some goods. And for another user, her behavior is like this. And so we see that in this case, these 2 users are very different in their behavior. And so in practice, we need to characterize a user not just using 3 numbers, but we need to take into account behavior in time, and we need to predict future values of this time series to better, treat users and optimize the value from them. Okay, and so what we can do in this way? First of all, each time series characterizing a user, when a user make an order, we can represent as 3 time series this is the time series of recency, this is the time series of frequency, and this is the time series of monetary. So this is how value of money from a user change with respect to time. This is how frequently a user make orders, how this quantity change in time, and this is the characteristic which characterize when the last time the user make an order. So each user is characterized by this time series, 3 time series. And then the question is, how we can characterize this time series so that we forget about their, subject domain, but we define features which do not depend on the subject domain. And we can use for this topological data analysis. The first step would be, we have a time series, and we convert this time series into a sequence of high dimensional vectors. So for this, we take this sliding window of, say, length 30 days, and we move across the time series. And so we obtain a sequence of high dimensional vectors, and that's it. We represent each time series by a sequence of high dimensional vectors. And because there are significant dependencies between consecutive values of the time series, then these high dimensional vectors will be located in the high dimensional space near some nonlinear near some nonlinear manifold. And actually, there is a mathematical theorem which states that there is a one-to-one mapping between statistical properties of the time series, like memory, length of the memory, and other properties, and the properties of this manifold. And so, by doing this, we reduce the problem of time series prediction to the problem of manifold estimation. So, if the manifold and each point on this manifold corresponds to some specific time window of the time series, and when we move across this manifold, this results in generation of the future values of the time series. And so if we estimate properties of the manifolds, we can predict future values of the time series. In order to characterize some invariant properties of the time series, it turns out that topology is a very efficient tool for that. The idea is as follows. First of all, what is topology? So topology is a special discipline in which it's an interesting joke. For topologists, this stuff and this cup, they are the same, because you can use a nonlinear transformation to get this cup from this Dunkin' Donut, right? However, if we look at this Dunkin' Donuts on a finer scale, we will see that it has a lot of holes here. And so, actually, real-world objects, they are discrete because they can have fine structure. And in practice, actually, often we deal with objects represented by such multidimensional points. And as I explained to you, we represent each time series by a point cloud. And because this point cloud belongs to a surface of the manifold, So by estimating some invariant properties of the manifold, we can characterize the time series. So this is the idea. Okay, returning to this example with Dunkin' Donuts, this is our points sampled on the surface of the Dunkin' Donuts. And if we put spheres in each of these points, then we see that, okay, if radius of spheres are small, then you see that they are not connected, and we get some cycles here and, for example, here. But if we increase radius of spheres, then these cycles disappear. However, we see that the only hole which doesn't disappear if we increase the radius of the spheres significantly, this is this central hole. And so the more we increase radii of the spheres, the less small holes we have here, but the central hole, it stays, I mean, it doesn't disappear. And it only when we increase radii of spheres significantly, this central hole disappears. So what does this mean? This means that in our data set of multidimensional points, there are different geometrical peculiarities, and some of these peculiarities are persistent, and some of these peculiarities, you know, they are noisy. Noisy to some extent. And so what we can do? We can, so the idea is as follows. As I said, we represent each time series by a sequence of high dimensional vectors, and we get a point cloud. This is the first step. The second step, we take this point cloud and we put a sphere in each point, and we start to increase radius of the sphere step by step. And then we calculate the number of holes we get. So, for example, in this case, we have only, say, 2 holes. But when we increase the radius of spheres, we get only 1 big hole, and these 2 small holes disappear. And so, in this way, we can characterize invariant properties of the manifold, which are persistent. In this, there is a special theory called calculation of persistent homologies. So I don't want to go into details. We don't have a lot of time, unfortunately. But as a result of this calculation, we get so-called persistent landscape, which can be formulated as follows. So here we depict radius of spheres, using which we cover the point cloud. And each of these you know, segments here, it corresponds to some hole, and the left point of this segment, it is when the hole appear, and the right point, it is when the hole disappear. And so we can relate each time series with such persistent diagram. And it turned out that using such persistent diagrams, we can efficiently characterize time series and automatically construct efficient features for the prediction of their future values. So I'll skip technical details on how this can be calculated. What I will show you is that the results are quite promising. So if we use topological features combined with these factors, with this RFM concept, then the accuracy increases significantly. So these are 4 different data sets for customer demand forecasting, and we showed that we can significantly improve accuracy if we use these topological data analysis features.